All right, good morning. Welcome all. We'll start in a minute. Do you have any question before we start? All right, good morning. Welcome all. We'll start in a minute. Sınavı bu hafta içinde açıklamaya çalışacağız. Well, okay, then let's start. So let me remind what we did last time before the review. This is lecture 13. So let us recall linear systems. We were solving linear systems. Well, we have such an equation: x prime is equal to a times x. A is an n by n matrix. It is a matrix, usually with constant coefficients. Well, to solve this equation, last time we defined this fundamental matrix, and exponential matrix is a fundamental matrix, remember. So find, to solve, star, find e to the ax, at, sorry, e to the, right, e to the ax, let me say at here. Okay, so the columns of here, e to the at will be, they are in linearly independent solutions of this system of equations, right? This is an exponential matrix. It's exponential. Matrix, right? And let's call it phi of t. We call this phi of t, and the columns of phi of t, this matrix, are linearly independent. We showed this. And we have n linearly independent vector functions coming from this columns, which implies that general solution to general solution to star is, it can be written as x of t, which is, well, you take the columns and consider the combination, linear combinations of columns. This is basically e to the at, which is phi of t. And the combination, you can write the combinations of the columns with, you multiply this matrix with a constant vector. Okay, so it's like C1, C2, Cn, okay? So this gives a combination of the columns, right? You can check this yourself, which is basically the combination of linear combination. Let's see, linear combination of columns. Okay, so you do that to find the general solution. Well, the problem is, how do you find this exponential matrix? When A is a diagonal or diagonalizable, we know how to do that, right? So when A is diagonal, that was case 1. We covered this case. Or diagonalizable, that means you multiply this matrix from left and right, and you make a diagonal matrix. You get a diagonal matrix. Diagonalizable. This is case 2. We did some examples with that as well. We're done, right? We know how to find, maybe let's write here. We know how to compute e to the at exponential matrix. Okay, now we will do the remaining case. So the remaining case, this is case 3, by the way. Okay, so now we consider this case when A is not diagonalizable.
Hocam, burada tekrar için ufacık bir şey sorabilir miyim?
Tabii.
Not diagonalizable determinantının 0 olduğu zamandı, değil mi?
Değil.
Neydi hocam?
Değil. Yani mesela şöyle bir şey olabilir. Yani konuşacağız zaten bununla ilgili.
Tamam o zaman.
Ama şöyle bir şey olabilir mesela 1, 0. Bu matrix diagonalizable değil. Ama determinantı da 0 değil. Determinantta direkt bir bağlantısı yok. Maybe let me explain this. Not diagonalizable, this is equivalent to say that A doesn't have n linearly independent eigenvectors. Okay, so we don't have enough linearly independent eigenvectors in that case. Remember, if the eigenvalues are all different, if you have different eigenvalues, it's always diagonalizable, but we don't have the converse. Sometimes we have same eigenvectors and it is still diagonalizable. For instance, the identity matrix. Identity matrix is diagonal, right? And then diagonalizable. But it has repeated eigenvalues, right? So maybe let me remind also this. Another fact. If A has different eigenvalues, it's an n by n matrix, has n different eigenvalues, then A is diagonalized. But there are other cases when your matrix can be diagonalizable. And for instance, identity matrix is diagonalizable, but we have the same eigenvalues. That's also possible, okay? That's what I'm saying. But if you have different eigenvalues, it's for sure it is diagonalized.
Tamam hocam. Direkt eigenvalülerle alakalı.
Evet, biraz onunla alakalı.
Tamam. Teşekkür ederim hocam.
Well, let's now talk about non-diagonalizable case. Non-diagonalizable means basically we don't have enough eigenvectors, and that means basically you cannot diagonal by multiplying from right and left. You cannot make it diagonal matrix, okay? You cannot make your matrix diagonal. But still we can do something. We can make something similar to the diagonal matrices, and these are called Jordan forms. We will talk about this now. Let's write this definition. A matrix J is, let's call Ji, is called a Jordan block okay, it's a Jordan block if it has the following structure. If it is of the form something like this, we have on the diagonal, we have, let's say, some numbers, lambda I, let's say, and same here. Maybe let's write like this, lambda I 1, 0, 0, then 0, lambda I 1, 0, 0, and it goes like that, okay? So basically, lambda I on the diagonal, and above this diagonal, we have 1, 1, and so on, okay? Here we have 1. And the rest is 0. Maybe let's put a big 0 here, like that. And this, okay? So basically, again, here, what is a Jordan block? It's a matrix, looks like this. We have on the diagonal, we have this lambda i's, okay, some numbers like that. Just above the diagonal, we have all ones here, okay? And it's called a Jordan block. Well, what's the Jordan form? Jordan form is the following. So a matrix is in Jordan form if it looks like the following. We have, let's say, this is in the Jordan form. That means we have Jordan blocks on the diagonal. So we have something like this, for instance, J1. It's a Jordan block. It's a matrix. Another Jordan block here, it's J2, okay? And you go like that, J, let's say K. So you have some Jordan blocks. And other than this, you have zeros everywhere. So this matrix is in the Jordan form, okay? Let me give some examples.
Sorry, can I ask a question?
Sure.
But in previous example, we had also sorry, a lot of ones.
Yeah, in the previous example, it's a Jordan block. This is a Jordan form. That
Okay,
means
thank you.
each of them, J1, is a block, okay?
Thank you.
Let me give an example and you will get it better. So, for instance, let's say 2, 2, 1, 0. It's a Jordan block, okay? And let's put here, for instance, 1. Let's use another one. 3, 3, 3, okay? And then 1, 1 here, and 0, 0, 0. So we have 2 Jordan blocks here. And all others are 0. It's a 5 by 5 matrix, okay? So you see here, this matrix is in Jordan form. Okay. Yeah. So this is a Jordan block here. And this is another Jordan block here, okay? And it's a 5 by 5 matrix at the end. Is that clear? Okay. So we have 2 Jordan blocks in this matrix. Well, we'll talk about why we consider Jordan forms. These are like, as I said, they're like in the diagonal case, they look like diagonalizable matrices. Okay, you can exponentiate easily in this form. That's why we consider Jordan blocks. Yeah, in this case, eigenvalues are repeated. Yeah. So the eigenvalues, if you compute the eigenvalues of this matrix, we have 2 repeated 2 times and 3 repeated 3 times. That's right. Well, okay. Now let's write this important theorem here. We will not prove it, but let's write what it is. It says you can always get the Jordan form of any matrix. Okay, so for any matrix, for every matrix A, m by n, there exists an invertible P such that P inverse A P is in Jordan form. So basically, multiplying from left and right, you can put your matrix in Jordan form. Right, so repeated eigenvalues are considered in this case, right? So now we are doing repeated eigenvalues, right? And the question is here, how do you find this P, right? The question is, how do you find J and P. Right? This is similar as in the diagonal case. It's about eigenvectors, but the bad thing here is we don't have enough eigenvectors here, linearly independent eigenvectors. Remember the diagonalizable case. In that case, we have enough linearly independent eigenvectors, and using those eigenvectors, we form our P. In that case, we don't have enough linearly independent eigenvectors. So we will talk about generalized eigenvectors in that case. Let's talk about this. So suppose, let's start with a simple case, Jordan block case. Okay, so suppose J is a Jordan block. It's like this: lambda 1, 0. Okay, let's write a couple of those terms here. Okay, and next 0, lambda 1, 0, and so on. 0, 0, lambda 1, so on, and it goes like this. And at the end, this is lambda. Here is 1, and here is 0. Okay. Let's say you have a Jordan block like this. It is a Jordan block. And let's say we find the P. We don't know what it is, but let's say we have a P. And P is, remember, P is that makes your matrix, that puts your matrix in Jordan form. Okay, this is P. And let's say P has the columns V1. These are the column vectors, V2. Okay, and Vn. And we try to understand what are this V1, V2, Vn, okay? And remember that P, here we have this relation, P inverse A. P is equal to J, right? That's the relation. And this tells you what? This tells you basically AP is equal to P times J, right? P times J. Well, let's write this relation. What is this? AP is equal to P times J. So AP is what? It's A times this matrix, V1, V2, and so on. Okay. Well, this is equal to P times J, V1, Vn, times J. What is J? J is this, right? We had this matrix. Let's write it. Lambda 1, 0, 0, 0, lambda 1, 0, 0, 0, lambda 1, and so on. Okay. Maybe let's 0 here, 0 here, 0 here, and so on. Right, we have such a matrix. Let's see what we get from this equation. The first one here, this one here, on the left-hand side of the equation, we get what? We get A times the first, you multiply A with the first here column, and you get A times V1. On the right hand side, here, let's see what we get. It gets you basically lambda here, this times this one, okay? Which is basically lambda times V1. And this is the equation of what? It tells you basically lambda is an eigenvalue and V1 is an eigenvector, okay? So this tells you lambda is an eigenvalue and V1 is an eigenvector. Okay, so it tells you this. Let's continue with the second one. So you multiply now this one with V2, A times V2. And on the right hand side, we get what? On the right hand side, it's the following. Maybe let's write V2 here as well. There is V2 here. So you take this column and this one, okay? No, the whole thing like this, yeah. So you take, well, how do you multiply two matrices? Like, it's like multiplying by matrices. It's not that explicit, but you take this whole thing and you multiply with the column, okay? So you take this row, like the row of columns, okay? Think of like that. So when you take the whole thing here and multiply with this one, what you get is basically V1 plus lambda times V2. Well, what is this? You can write this as well in this form, A minus lambda I. So you take this to the left-hand side, okay? Lambda I V2 is equal to V1. All right. So basically V2, you can find V2 by solving this equation. V1 is an eigenvector, so you find eigenvector. And how do you find V2? The second column, you solve this equation and find V2, and this is called the generalized eigenvector. It's not an eigenvector anymore because on the right-hand side, we don't have a zero vector, right? So here we have something non-zero. That's why V2 is not an eigenvector, and we call it generalized eigenvector. So let's continue this process. What you do next is, instead of this one, take now the third one here, okay? And it gives you what? It gives you the following. A times V3, for instance, it's gonna be V2 plus lambda times V3. And this tells you, again, A minus lambda I V3 is equal to V2. So in the previous step, you find V2, now use V2 to find V3, okay? And you continue like this and find all the columns. So A times Vn is equal to Vn minus 1 plus lambda Vn. And this implies basically A minus lambda I Vn is equal to Vn minus 1, okay? And you can find n linearly independent vectors by doing that, okay? Well, you can either follow this, okay, with that one, or this is equivalent to the following, okay? So maybe let's put here star, double star. So the system double star is equivalent to, well, we first have A, V is A minus lambda I, V1 is equal to 0. Okay, this is eigenvalue and eigenvector. To find the generalized eigenvectors, we had this, right? A minus lambda I V2 is equal to V1. But that means what? Let's multiply both sides with A minus lambda I. So this implies A minus lambda I square times V2 and A minus lambda I times V1 on the right hand side, which is 0. So this implies that, right? And similarly, A minus lambda I cube V3 is equal to 0. And you continue this process, and A minus lambda I to the n Vn is equal to 0. You either solve this system or the previous one. They are the same, okay? So this two systems here and here, they are equivalent. You either work with this one or this one. Is it clear what I am saying? And so what are V2, Vn here? Maybe let me write here. Note here. So V1 is an eigenvector. We already discussed this. Eigenvector. V2, Vn. These are called generalized eigenvectors. Generalized eigenvectors, okay? Any question with this? We will do an example, don't worry, it looks like complicated, but it's not. When we do the examples, you will get it better, okay? All right, let's do an example. Okay, so find the Jordan form of the matrix A, which is 1, 1, 1, 2, 1, -1, -3, 2, 4. To find the Jordan form, we need to find generalized eigenvectors, right? First, we need to find the eigenvalue. So let's do it. Well, the eigenvalues find the determinant A minus lambda I, which is 1 minus lambda 1, 1, 2, 1 minus lambda minus 1 minus 3, 2, 4 minus lambda. Okay, we find this determinant and we find the lambda from this equation. Well, you can do it yourself. This determinant will be, check this yourself, lambda minus 2 cube. Okay, that means lambda is an eigenvalue, 2 is an eigenvalue with is an eigenvalue. It's repeated and we say it's an eigenvalue with multiplicity 3. Multiplicity 3. That means it repeats 3 times, okay? Lambda minus 3 to cube. It repeats 3 times. So we have this. Well, now let's find the eigen vector for this lambda. To find the eigenvector, what we do is, remember, you put lambda is equal to 2 and solve the following. 1 minus 2, well, maybe let's write directly. 1 minus 2 minus 1, 1, 1, 2, minus 1, minus 1, minus 3, 2, 2, 0, 0, 0, right? We solve this system. Well, we do the row operations. What you can do is, for instance, you can get rid of this 2 here and 3 here at the same time. It's like, okay, let's do it in that way. Minus R1, you multiply the first here with negative 1 to make it 1. And then 2R1 plus R2 will go to R2. And minus 3 R1 plus R3 will go to R3. And from this, you will get basically 1 minus 1 minus 1, 0, 0, 1, 1, and 0, minus 1, minus 1. Okay. And now this, you can make it better. 1 minus 1 minus 1, 0, 1, 1. You add R2 and R3, you get 0, 0. So this is R2 plus R3 will go to R3, and we get this right, which says basically V2 plus V3 is equal to 0, and the first row will tell you V1 is equal to V2 plus V3. You can either say V3 or V2 is free. It doesn't make any difference. Let's say V3 is free. Say V3 is K, okay, which is non-zero. And then this tells you V2 is minus K, and V1 is 0. So from this, the eigenvector V, let's say superscript 1, is K times 0 minus 1, 1. Okay, this. We don't take K when we write the matrix. We don't need it. Okay, we just take one eigenvector when we write the matrix. So we will take K is equal to 1 in that case. So this is an honest eigenvector. And let's find the generalized eigenvectors. Remember the equation here. What you do is either you work with this one here, or the other one. So let's use, let's work with the first one, because taking the square of matrices is not easy. So I will work with that one. A minus lambda I times V2 is equal to V1. So to find V2, we will solve A minus lambda I V2 is equal to V1. V1 is basically, you can take this as 0 minus 1, 1. Okay, take one of those. K is equal to 1. And let's find V2. Well, okay, let's do it. So A minus lambda I is about the same, right? Maybe let's put, instead of lambda here, lambda is 2, right? It's 2. So the same matrix, minus 1. Let's minus 1, 1, 1, minus, so 2 minus 1, minus 1. And minus 3, 2, 2. But on the right-hand side, now we have this vector instead of 0. 0 minus 1, 1. So we solve this system. Okay. Well, what you can do is you can get rid of this entry, and you can make it this 1 by multiplying minus 1. So minus R1 and 2 R1 plus R2 will go to R2 And at the same time, well, we do the same thing basically. Minus 3 R1 plus R3 will go to R3, and you will get this 1 minus 1 minus 1, 0 1 1, 0 minus 1 minus 1, and these are 0 minus 1 1. Okay. And again, you do this R2 plus R3 will go to R3, and we get simply 1 minus 1 minus 1, 0 1 1 minus 1, 0 0 0 0, which tells you basically V2 plus V3 is equal to minus 1, and V1 is equal to V2 plus V3. So V2 plus V3 is minus 1, okay, from here. So V1 is minus 1, and one of them is free, V2 or V3. Say V3 is free. So say V3 is K. You can also do with V2, doesn't make any difference. And then V2 is from here now, minus 1 minus K. So the vector is basically, which is V1, V2, V3, and this is minus 1, minus 1 minus K, and this is non-zero, and K. Okay. Well, in that case, it can be 0, sorry. It can be 0 because the thing is, you don't get a 0 vector when K is equal to 0. So here K can be any real number, okay? Because you don't get a 0 vector when K is equal to 0, so you can choose K is equal to 0. There's nothing wrong with that. So choose any K here, and we will get, choose any value for K to get V2. Say, for instance, K is equal to 0, and you get what? You get V2 as minus 1, minus 1, 0, okay? This one. We get this vector. So we find V1, we find V2. Now let's find V3. To find V3, we will solve this system, A minus 2I V3 is equal to V2. So you do basically the same thing. So you solve it, and a minus lambda I. So we get basically this 1 minus 1 minus 1, same matrix. The right hand side will be different now. Sorry, minus 1. Right. 1, 1, and 2 minus 1, minus 1, minus 3, 2, 2, and V2 was minus 1, minus 1, 0. Then you solve this in a similar way. I will not do it, okay? So solve it, and maybe let me write the resulting matrix. When you do the row echelon form, you will get something like this. 1, minus 1, minus 1, 0, 1, 1, 0, 0, 0, 1, minus 3, 0. That means basically V2 plus V3 is equal to minus 3, okay? And V1 is equal to V2 plus V3 plus 1. This follows from the first row, which is minus 2. All right. You put this here, and you get this minus 2. Either V2 or V3 is free. Say again, V3 is free. And this implies V3 here is minus 2, minus 3 minus, say maybe V3 is equal to K. Okay, K, and this is K. And again, you can choose K is equal to 0. Choose any K you want. That doesn't make a 0 vector, okay? Choose K is equal to 0, and then you get V3. Take this, okay? Take V3 as minus 2, minus 3, 0. So we find all eigenvector and generalized eigenvectors, V2 and V3. Now we can write the matrix J and P, which makes our matrix in the Jordan, which puts our matrix in Jordan form. So what is P here? P is, remember, it was V1, V2, V3. Okay. And this is, what is V1? Let's recall V1. 0 minus 1, 1. 0 minus 1, 1. And V2 was minus 1, minus 1, 0. And finally, V3 is minus 2, minus 3, 0. Okay. And what is J? J is, it's the Jordan block. We have only one eigenvalue, so we have, well, in principle, it's either this 2, 2, 2. There is only one Jordan block, okay, in that case. This is one possibility, or it could be like this as well. You have two Jordan blocks, 2, 2, 1, 0, 2. So we have two Jordan blocks, okay? And the remainings are 0, like that. So let me highlight here. This is one Jordan block. No, sorry. There's only one Jordan block here, which is the whole thing, okay? And in that case, there are two Jordan blocks. One is this, the other is this one. They are both possible in principle, but in this case, this is not possible. 2 blocks. And this is 1 block. This is not possible. The reason is each Jordan block will give you one eigenvector. And there is here only one eigenvector, one linearly independent eigenvector. That means there must be one block, okay? Not possible because there is only one eigenvector. Okay, each block will give you an eigenvector, but here we have only V1 as an eigenvector, linearly independent eigenvector. We solve it and we find that there is only one eigenvector. That means there cannot be more than one block, okay? So this is basically another possibility. Let me first get rid of this. And J must be this one, okay? The first one. Okay, there's a question. Hocam, can one be below? No, these are all possibilities. Remember, on the diagonal, we have only eigenvalue, okay? 1 is not an eigenvalue, so you cannot put 1 in the diagonal. Here, there's another question, V2 and V3, are these eigenvectors? No, they are not eigenvectors, they are generalized eigenvectors, okay? Generalized eigenvectors is something else, we define it here. They are basically the solutions of these equations, okay? So they are not eigenvectors. Here, there is only one eigenvector, V1. V2 is a generalized eigenvector. V3 is same, okay? Right. Any other question? Comment? We will give a break here for 10 minutes.
Hocam ben bir soru sorabilir miyim?
Maybe before your question, let me finish this. So, and in that case, J is equal to P inverse A P, okay? So we know what P is, we know what A is, you can find the inverse, and when you do that, you get this Jordan block, okay? Yes, question?
Hocam neden sürekli eşalon form yapıyoruz? Upper triangular form kullanmıyoruz mesela.
Ne kullanmıyoruz?
Upper triangular form.
Kullanabiliriz yani, o da olabilir. Çok öyle bir tercihimiz yok. Sadece sistemi çözmeye çalışıyoruz. Yani eşelon mesela bir yerde galiba tam da getirmedik aslında. Her yerde getirdik mi ya? Yani eşelon form daha garanti bir çözüm verdiği için onu kullanıyoruz. Yoksa nasıl çözerseniz çözün, onun bir önemi yok.
Sınavda fark etmez yani.
Hayır, yok. Yani yanlış yapmadığın sürece fark etmez. Ama
Evet.
soruda özellikle row echelon formu kullanarak bulun falan diyorsa, o zaman tabii row echelon forma getirmek durumundasınız, ama genel olarak böyle bir şeyde, hani soru o değilse istediğiniz gibi çözebilirsiniz.
Tamamdır hocam, çok teşekkürler.
Any other question? Okay, let's give a break for 10 minutes and let's meet at 11:50.
because this is not a lot of FPSs. Yeah, doing the whole map. Yeah, okay. I mean, in fairness, this is running 720p, mostly low, but
All right, let's continue. Um,
Hocam ben başlamadan bir şey sorabilir miyim?
Sorabilirsin tabii.
Burada Jordan block'un ne olduğunu hani tek eigenvalue olduğu için kendimiz yazabildik ya. Hani
Evet.
öyle p-1 AP yazmamıza
Aha,
gerek
evet.
kalmadı aslında. Yani bu işlem için bütün o matrisleri çarpıp Jordan block bulmamıza gerek yoktu değil mi? Biz kendimiz hani sıfırları, ikileri, birleri yerleştirerek
Evet.
bulabilirdik.
Evet, evet. Yani öyle yaptık zaten aslında. Jordan bloğu bulmak için doğru diyorsun. Ama o P matrisine de ihtiyacımız olacak. O yüzden gerekiyor onu bilmemiz. Yani denklem çözerken o P matrisi sadece Jordan blok yetmiyor.
Ha, ben şey gibi düşünmüştüm. Mesela hani teoretikle olabilecek Jordan block vardı ama bu durum için iki farklı eigenvalue olmadığından olamadı ya.
Aha.
Hani acaba oradaki hani ufak Jordan block'la 2'ye 2 Jordan block'un yerleri değiştiği zaman mı? Hani
O bir şey
öyle
fark
şeyler.
etmez. O bir şey fark etmez. O iki bu Jordan bloğun yeri değiştirse de e, yani hani öyle olsa bile o yer değiştirme şeyi çok fark etmiyor ama şimdi göreceğiz bu denklem çözerken o P matrisine ihtiyacımız olacak. Yani Jordan bloğu blok haline getiren matrise.
Ha, anladım. Biz aslında Jordan Bull'u ama kendimiz böyle şey yapabiliyoruz, oluşturabiliyoruz.
Evet, Jordan Block'un nasıl olduğunu görmek için çok da P'ye ihtiyacın yok aslında. Ama biraz işte hani iki durum olabilir. Mesela bir öncekinde onu görmek için en azından bir eigenvektör olduğunu bilmen gerekiyor. Hani.
Tamam,
Hı
tamam hocam.
hı.
Teşekkürler.
Şimdi mesela ondan bahsedeceğiz. Now we will talk about exponentiating Jordan forms. So let's do this. Exponentiating Jordan forms. Well, let's say your matrix is in Jordan form and you write A as P, J, P inverse, okay? And then what is A to the K? A to the K is basically P, J. This is like in the diagonalizable case. So you multiply this with K times P, J, P inverse, right? And you continue this stuff, P, J, P inverse. So what you see here is there are cancellations, okay? So these will all cancel out. And what is left here? We are left with basically P times J to the K times P inverse, okay? This. Well, then E to the AT, the exponential matrix is now, it's by definition, AT to the K, right, over K factorial. K is from 0 to infinity. And you can, now we know what is A to the K is. You can write this like, take T out. So A to the K is P times J to the K P inverse times T to the K over K factorial. You can take P out of this sum because it doesn't depend on K. So it is P times the sum, well, J to the, maybe let's write it like that, J times T to the K over K factorial times P inverse, right? Like that. But the middle term here, the sum, is nothing but E to the JT. So P E to the J T P inverse. So this tells you basically if you can exponentiate the Jordan block or Jordan form, then you can exponentiate any matrix, okay? So if you know what this here, if you know what this is, you know what E to the AT. Because we can find P, right? Like in the previous example, and you find the exponential of the Jordan form, E to the JT, and multiply with P and P inverse, and you get this. All right. And the question is, how do you exponentiate the Jordan form? Let's do this with a Jordan block. It's a fact. I will not prove it, but it's not difficult to show. When you have a Jordan block like this, let's say lambda 1, 0, 0, 0 lambda 1, 0, and so on. Okay, like this. Then E to the JT, maybe let's write it here. E to the JT is E to the lambda t times this matrix. We have 1 t squared over 2. This is like, remember the exponential e to the t, right? We had these terms. t squared over 2 factorial actually, and then 3 factorial and so on. So this goes to t to the n minus 1 over n minus 1 factorial. Okay, and the next it's 0, 1, t. You continue like in the first case, in the first row, t squared over 2 factorial, which is 2, and t to the n minus 2 over n minus 2 factorial. And you do this, okay, for all rows. Well, diagonal will be again 1, okay, here, and the rest is like this. It's an upper triangular matrix. The below the diagonal, everything is 0. Above the diagonal is all 1. And next to diagonal, we have like this Taylor series expansion of e to the t. Okay. Let me give an example, maybe. Well, this is for one Jordan block. If you have multiple Jordan blocks, you basically do this for each block, okay, and you will get the result. Let me do a quick example. Let's say j is equal to and 3, 3, 3, 1, 1. I'm sorry. 1, 0, 0, 0, 0. We have 2 Jordan blocks here, and all others are 0. Okay, 0 here, 0 here. It's a 5 by 5 matrix. Okay, so what is e to the jt? Well, from the first one, it follows from e to the 2t. From the second one, it follows from e to the 3t. Okay, like this. And we have the following. 2 and 1, sorry. 1, 1. Okay. What was it? Well, basically t, right? T, 0. This is the first block, right here. The second block will be 1, 1, 1. This is t squared over 2. Here t. Okay, like this. 0, 0, 0. And here is the second block for eigenvalue 3. And all others are 0. 0 here, 0 here. Okay. Any question with this? Now let's solve a system of equation with repeated eigenvalues. Let's do this with an example.
Hocam, ikinci example'a başlamadan önce, şimdi bu Jordan bloğu bulduk ya.
Evet.
Sonra bunu şey soruyorum, yani böyle aslında bulmaya çalıştığımız hani x'ler falan var ya, hani
Aslında
denklemi
bulmaya
çözüyor.
çalıştığımız şu E üzeri AT'yi bulmaya çalışıyoruz. Bunun kalımları şey olacak, çözüm verecek değil mi? Yani kalımları çözüm verecek şu demek değil mi? Bunun
Hmm.
kalımlarının kombinasyonunu yazmak aslında bu çarpı C1, C2, Cn diyelim. Bunlar sabit. Bu genel çözümü verecek.
Tamam. Bunu da E üzeri AT'de bu Jordan, exponential Jordan'ı işte P ve P üzeri eksi 1 ile çarpıp bulacağız.
Aynen öyle. Bak,
Onu
bu
da C1, C2 ile
evet,
çarpacağız. Tamam hocam.
evet.
Teşekkürler hocam.
Hı hı.
Hocam ben de bir şey soracaktım.
Tabii.
O zaman mesela iki tane Jordan block barındırdığımız zaman iki ayrı bloğun da ilk elemanlarını mı direkt üstel fonksiyonun üstüne yazıyoruz? Ondan sonra direkt
Ya,
az önce
bir
bahsettiğimiz
dakika,
forma geçirmek
pardon
mümkün mü?
bu yanlış oldu. Özür dilerim. Ee, şu şöyle olacaktı. Yani E üzeri 2T'yi sadece şununla çarpacağız. Tamam, şuraya. Bu E üzeri 2T. Şu da E üzeri 3T. Yani ayrı ayrı çarpmamız lazım. Pardon. Bunu
Yani aslında bununla alakalı evet. O zaman böyle bir durumda ilk baştaki katsayıyı hani üstel fonksiyona çarptığım zaman direkt kalanı işte bir T formunda aynı direkt buna indirgiyoruz diyebiliyor muyuz? Yani sadece ilk katsayıyı üstelin üstüne yazdığımız zaman.
anlamadım. Bir daha sorar mısın?
Yani mesela son example'da Jordan formunda işte
Aha.
ilk bloğum 2 ile ikincisi 3 ile başlıyordu ya.
Evet.
Direkt 2 ve 3'ü ayırdığımız zaman o
Hı hı.
ikinci yani en son haldeki bloktaki 1 T 0 ve 1'li şekli direkt geliyor diyebiliriz yani öyle mi?
Tabii. O şuradan geliyor. Bir üstteki fact yazdık ya.
Hı hı.
Yani şu. Değil mi? Şu form.
Aynen yani direkt oluyor o zaman. Peki
Evet.
o zaman eigenvalue'larım burada 2 ve 3 diyebilir miyim?
Diyebiliriz tabii.
Hı, tamam.
2 kere tekrar ediyor. 3 de 3 kere tekrar ediyor. Ama
Hı.
şeyi bilmiyoruz. Kaç tane eigenvektör var onu bilmiyoruz.
Ha, evet tamam. Okey.
Yani eigenvektör mesela birden çok da olabilir. Repeated eigenvalue için. Onun için çözmen gerekiyor.
Anladım hocam. Çok teşekkürler.
Gerçi burada biraz biliyoruz çünkü Jordan Block'a bakarsak burada bir tane Jordan Block var. Bir tane Jordan Block olduğu için bir tane eigenvektör var. Burada da yine bir tane Jordan Block var. O yüzden burada da bir tane eigenvektör var. Yani aslında onu da biliyoruz. Eigen. Ama şöyle olsaydı mesela bunun yerine 3 şöyle bir şey olsaydı 2 tane block olsaydı şöyle. Geri kalanlar 0. Bunda mesela 2 tane eigenvektör olacaktı. Linearly independent. 3'e karşılık gelen.
Hı.
Her blok bir tane linearly independent eigenvektör veriyor. Tamam.
Tamam hocam. Çok teşekkürler.
Any other question? Well, we correct this, right? This e to the 2t, it's for only for this matrix here, okay? Not the whole thing. And the other one here, we have e to the 3t, okay? It's important. All right, let's look at this example now. Solve the system x prime is equal to 1, 1, 1, 2, 1, minus 1, minus 3, 2, 4, x. Okay. Well, this is the same matrix, remember. This is A, and we already find P and J for this A. So we will use previous example. So by previous example, A was this. A is P times J times P minus 1, where P is this. We find this, right? Eigenvalue and generalized eigenvectors and eigenvector. The first one here is the eigenvector, and the others are generalized eigenvectors. Okay. And what was J? J was this. We had 2 as the eigenvalue, 1, 1, 0. So we don't do this again. The first entry is -1. Let's see. Okay. I believe you. So this is -1. Okay. Thank you. All right. So we get this P and J. Then what is e to the JT? E to the JT is, by the fact above, it's e to the 2t times 1, 1, 1, always 1, right? E to the 2t times this matrix, t square over 2, t, and 0, 0, 0 everywhere. Okay, this. Okay, let me check. What was it? 1, 1. No, that was 2 minus 1 minus 1. No, that was 1. Check A in the previous example. Maybe you, right, you consider the next step, right? This is the original A. It's that one. I checked that. Okay. All right. Well, this is e to the JT. And what is e to the AT? So e to the AT, this is the fundamental matrix or exponential matrix, same here. Which is P times e to the JT times P inverse. Well, the trick here is the general solution is what? The general solution is to star. So what is star here? Let's call it star here. Okay. To solve this, we use the columns of fundamental matrix. So x of t is basically e to the AT. The columns of this, the combination of columns, you can write it like this. It's a 3 by 3 matrix. So you can write this with C1, C2, C3. Okay. But what is this? Well, this is basically P times e to the JT times P inverse times C1, C2, C3. The thing is, when you multiply this P inverse with this column vector, you get a constant vector, right? So it's a constant vector. And you can call it, say for instance, K1, K2, K3. That means we don't have to deal with the inverse P. You don't have to find inverse P because you multiply two constants and you get another constant, right? So this implies basically no need to find P inverse, okay? You can continue with K1, K2, K3 instead of C1, C2, C3 because these are arbitrary constants, right? So this tells you basically xt is P times, what is P? Okay, P is maybe let's write like this first. P times e to the jt times k1, k2, k3. And more explicit, what is P? P is 0 minus 1 minus 2 minus 1 minus 1 minus 3 1 0 0. This is P. What is e to the jt? E to the jt is e to the 2t times 1 t squared over 2 0 1 t 0 0 1. Okay, and you multiply the whole thing with k1, k2, k3. And let's first deal with, maybe you take this out and multiply this two, okay, these two matrices, and you get the following. Zero minus 1 minus t minus 2 minus 1 minus t minus 1 minus t squared over 2 minus t minus 3 1 t squared over 2. So you multiply these two matrices and you get the following times k1, k2, k3. Well, you can write this in better form. What you do is basically you look at each column here. So this is basically the combinations of the columns. So it's a multiply with e to the 2t here, okay? So the first column is e to the 2t times the first column of the matrix. So 0 minus e to the 2t, e to the 2t, times k1 plus k2 times, now use the second column, minus e to the 2t and minus t plus 1, let's write it like this, e to the 2t and t times e to the 2t. And the last column, okay, e to the 2t minus t plus 2 e to the 2t minus t squared over 2 plus t plus 3 e to the 2t. Yeah, right. T squared over 2 e to the 2t. Okay, here k1, k2, and k3 are any real numbers. These are constants, okay? So we get the general solution by this. Any question with this example?
Hocam bir şey sorabilir miyim?
Tabii.
Biz normalde matris çarpımı yaparken ilk başta ilk matrix'in row'uyla diğerinin column'ını çarpmıyor muyduk? Burada niye
Evet.
row column gittik?
Ona denk geliyor. Mesela şimdi şu son işlemi diyorsun değil mi? K1, K2, K3 ile çarpmayı.
Evet.
Mesela bir örnek verelim. İşte A, B, C, D. Tamam mı? Bunu K1, K2 ile çarpıyorsun. Nedir? Bakalım. Ne yapıyorsun? K1A artı K2 C diyorsun değil mi? Sonra diğeri de ne olacak? K1B artı K2D.
Ha evet, ona denk gelmiş o
Ona
zaman.
denk geliyor değil mi? K1 çarpı AB artı K2 çarpı C'de. Tamam mı?
Tamam hocam, teşekkürler.
Bunu tabii genelleyebilirsin. 3'e 3, 4'e 4 hepsi için doğru. Any other question? Well, okay. Now we will do non-homogeneous systems. So we are done basically with homogeneous systems. We covered different cases, right? And finally, we're done with repeated eigenvalues. Here, the matrix A has repeated eigenvalues, and we deal with this case using the Jordan form. We exponentiate our matrix. Nice thing here is we don't have to compute P inverse. Computing P inverse is tough. It's a 3x3 matrix. Even with 3x3 matrix, the inverse is not very easy to compute. You can do it, but it will take some time. But you don't have to do it because you multiply this with another constant vector. So you get another constant vector. That means you can work with the resulting constant vector K1, K2, K3, and you don't need P inverse. Okay, so this is a shortcut here. All right, let's talk about in the remaining 10 minutes non-homogeneous systems. 7.9. Non-homogeneous and we use here the variation of parameters method. The method we will use here is called variation of parameters. Okay. So our purpose is solve such a system X prime. Earlier we solved such systems X prime is equal to A times X. Now we have plus B. So X is a vector, A is a matrix, n by n matrix, and B is here, it's a vector function. It's an n by 1, okay, matrix, or it's a vector, okay, column vector. Well, let me recall what we do in the homogeneous case. So recall that the fundamental matrix it's, let's call it psi t, is, well, basically the fundamental matrix, you can take either e to the at, but you can also take without p inverse, because we don't need p inverse. So let's write like this: p times e to the jt, right, solves the system x prime is equal to ax, the homogeneous system, let's say, solves the homogeneous system by, how do you solve it? Well, it's basically, the solution is given as in the example, psi t times a constant vector, c1, c2, c3, right? Let's call it c, the vector, constant vector. Now, for the non-homogeneous system, we want to change this constant vector, and we get a similar solution. So we replace c by a vector function v to get a solution of the non-homogeneous system x prime is equal to ax plus b in the form, like in the homogeneous case, we will have, instead of the constant vector c, we will write this like phi of t times v of t. The question is, what is v, right? But what is this non-constant vector in this case? How do you find this? And we have a nice theorem here. Which says basically all solutions, let me call here star, color, all solutions to star is given by x of t, which is psi t. Psi t, remember, it was, it's a fundamental matrix. You can find it in different ways. It's a fundamental matrix. Fundamental matrix means the columns are going to be the linearly independent solutions, okay? Times v of t, where vt is the integral psi inverse, the inverse of the fundamental matrix, times b of t. B of t is the non-homogeneous term here in the equation. Just here, okay? We use this in the solution. Okay? So we have this formula. You can check this yourself. You can put this back into the equation and you can easily see that this satisfies the equation, but I will not do it. So we have this nice formula to solve non-homogeneous systems. Let's do a quick example. So let us solve x prime is equal to 2, 3, 0, 1 x plus the non-homogeneous term e to the 2t and t here. So in this equation, this is my matrix A, and this is my non-homogeneous term B of t, the vector, okay? Well, let's find eigenvalues first. To find the fundamental matrix, let's find eigenvalues first and see if we have different eigenvalues. Then we are lucky, we can write the fundamental matrix easily. So eigenvalues basically determinant of A minus lambda I is 2 minus lambda 3 0 1 minus lambda. That means we have this is equal to lambda minus 2 times lambda minus 1. So lambda is equal to 1 and 2 are eigenvalues. 1 lambda 2 is equal. Maybe let's keep this order. I use here 2 first and 1 second. And they are different, right? So these are different eigenvalues. When we have different eigenvalues, remember eigenvectors, corresponding eigenvectors are linearly independent, and you can write the fundamental matrix easily. You don't need Jordan form, or you don't need to go with diagonalizable case. Okay, so we can do this in a simpler way. What we do is find the eigenvectors first. Well, eigenvectors corresponding to lambda 1 is equal to 2. We have, I will not do it, you can check this yourself. It's going to be k times 1, 0. And for lambda 2 is equal to 1, it's basically k times minus 3, 1. Then the fundamental matrices. So we have basically the solutions are e to the 2t times 1, 0. These are the solutions for homogeneous equation. E to the t times minus 3, 1. And the fundamental matrix psi t is, you write this in columns, e to the 2t, 0, minus 3 e to the t, yeah, right, e to the t, okay? So this is the fundamental matrix. Remember,
Hocam bir şey sorabilir miyim? Bölüyorum ama. Burada
Sor.
şimdi şeyleri yazarken, vektörleri yazarken yine lambdayı kullandığımız sıraya göre yazmamız gerekiyor,
evet,
değil mi?
aynen öyle tabii.
Tamam, tamam. Tamam, e üzeri 2t falan, hani eksi 3'ü sola alamayız. Tamam hocam, teşekkürler.
Evet, evet, evet. Doğru. Now, V is, remember, it was by the formula in the theorem, it was psi inverse t times B of t dt. What is psi inverse? You can find psi inverse easily. This is a 2 by 2 matrix. You replace the entries in the diagonal. So it's going to be e to the t here, e to the 2t here, and you take the negative of all other entries, 3 e to the 2t, t, sorry, and 0, and you divide by the determinant of psi, e to the 3t, 1 over e to the 3t, okay, this. Right, okay, good. Maybe you can simplify this. It's gonna be e to the, so you divide everything by e to the 3t, e to the minus 2t, 3 times e to the minus 2t, 0, and e to the minus t. Okay, we simplify the inverse matrix, and now let's compute this v of t. V of t is basically this matrix, e to the minus 2t, 3 e to the minus 2t, 0 e to the minus t, times b of t. B of t is what? E to the 2t and t. E to the 2t and t here. And dt, right? Well, let's compute this here. It's going to be, you multiply these two matrices, and it's going to be this, the following. 1 plus 3 t e to the minus 2t, and t times e to the minus t dt. And you simply integrate each entries here and do the integration by part. I will not do it here. Integration by part for the second, even for the first one, yeah, because we have t times something. You need integration by part. And it's going to be, the integral of the first one will give you t minus 3 over 2t e to the minus 2t plus a constant c1. The second one is the following, plus another constant c2, okay? Well, this is v of t. Well, so remember in the theorem, the general solution is psi t times v of t. So x, the solution is psi t times v of t. Psi t, we already have it here, right? So we put this back in. E to the 2t minus 3 e to the t, 0 e to the t. This is psi. V of t we just find out here. You can split this v of t in two parts. It's going to be easier to work. So first, write without the constant part. It's going to be t minus 3 over 2t e to the minus 2t minus 3 over 4 e to the minus t, 2t, and this is minus t. This is one thing, plus c1, c2. You will see why I do this. Okay. And basically, you multiply this one with that one, and plus this one with the constant here. So you get basically, when you do the first multiplication, you will get the following: t times e to the 2t plus 9 over 4 minus t minus 1. we call this particular solution, plus you multiply with the constant, and multiplying with the constant, remember, you take combinations of the columns here. So you take this column times C1 and this column times C2. So it's going to be C1 e to the 2t 0 plus C2 minus 3 e to the t e to the t. That's it. So we call this is a particular solution. We will talk about this later, okay? And this is the solution of the homogeneous part. Solution of x prime is equal to ax, right? And when you combine this two, you get the solution of the non-homogeneous equation. Any question here? Sorry, I'm out of time. So we stop here. Var mı sorunuz arkadaşlar?
Hocam burada sayı V ile çarptık ya, orayı kaçırdım sanırım. Orayı bir daha tekrar gösterebilir misiniz?
Sayı V ile çarparken V'yi ikiye ayırdık. Bir sabit kısım var şurada. Bir de geri kalan kısım.
Hı hı.
Sabit, sonra dağıttık onu. Hani arada toplam var ya. Hani bu şey gibi. A çarpı B artı C. Sonra şu matrisle şu matrisi çarptım. Görebiliyor musun?
Aynen. Tamam hocam. Şimdi
Şu matrisle şunu çarpınca şunu elde ettim.
tamam.
Tamam. Diğer kısımda ilk matrisle C1, C2'yi çarptım.
Tamam hocam. Teşekkürler hocam.
Tamam. Any other question? All right, let's stop here. See you on, Friday is off, holiday. İyi bayramlar arkadaşlar. Görüşmek üzere.
İyi bayramlar hocam.
Teşekkür ederiz hocam. Elinize sağlık.
İyi bayramlar hocam.
İyi bayramlar hocam.